Okay, picking up from where we left off, right? We're talking about this example of two students who come to the University of Memphis and they have the option of whether to buy health insurance, right? One of them does. Kudzar Kalat buys health insurance. Okay, so his treatment status of D is going to be equal to 1. And then Maria Moreno, she decides not to buy health insurance, so her treatment status is equal to 0. Now again, we're talking about potential outcomes here, right? So for Kuzdar, there's two things that could have happened with him, right? There's two basically alternate realities that could have been realized, right? Even if only one of them actually was realized, right? So it could have been that if Kuzdar did not get health insurance, his health status would have been out of 3. If he did get health insurance, which is what actually happened, his health status would be out of 4. So for Kuzdar, we say the treatment effect of health insurance is positive 1, right? It's actually a good thing for him to have health insurance. For Maria, on the other hand, she's just as healthy whether or not she gets health insurance, right? This is actually partly why she decided not to get it, right? Because she figured, well, I'm pretty healthy. Health insurance isn't going to do much for me. I think my treatment effect's probably going to be 0. And again, because we're talking about these potential outcomes, these alternate realities, right? We only have one reality, and that's going to be this one, right? The one in which we say, okay, we have one student, he went out and got health insurance, and his health, we can see it's going to be a 4, right? We can see that because he got health insurance. So this potential outcome under health insurance is what actually happens. Okay, so that's a 4. And we want to compare him to Maria, who did not get health insurance, and we see she's actually doing a little better. She's getting a 5 despite not having health insurance. So the purpose of this, again, is to show why a naive comparison of two people, and eventually also two groups, who differ in their independent variable status can lead us astray. Okay? So we want to say, and again, the whole point of everything we do is we want to use what we can see as an estimate of what we can't see. So what we want to know, which what we can't see, is this thing, this treatment effect, right? The difference in the unobservable potential outcomes for each of these people. Right? We want to know what is the effect of health insurance. But all we see is that, well, Kuzdar bought insurance, Maria did not. So let's try to reason about why it's a problem to just compare them naively. If we did that, just the naive comparison, okay, we're going to take y sub Kuzdar, so Kuzdar's actual health outcome, minus Maria's actual health outcome, right? From the table, 4 minus 5 rather, is minus 1. And so based on that naive comparison, we'd say, oh, look, turns out people who get health insurance are less healthy. Health insurance is bad for you, right? But that would be the wrong conclusion. We know that from the example, the way this is constructed, that there's actually a positive effect for Kuzdar and a 0 effect for Maria. So what we've shown already is that this simple comparison is going to be biased. Okay, it's not going to be equal to the truth. It's going to be biased in a particular way that we can kind of reason about and then try to correct. So to show this algebraically, what we can do is plug in y Kuzdar minus y Maria, right? The comparison based on the things we can see turns out to be equal to this. Why? Well, we know that given Kuzdar took the treatment, his actual outcome is equal to what his potential outcome is if he got the treatment, because the if is, actually what happens here. That alternate reality is reality. For Maria, likewise, she decided not to get the treatment, so her actual treatment, or her actual health value, is equal to what it would have been had she not gotten the treatment. So we can just simply say y Kuzdar minus y Maria is equal to y1 Kuzdar minus y0 Maria, or the difference in these two potential outcomes for these two people. Okay, so to see, again, to flesh out why this is still problematic, so once we write this, which is from the previous slide, we can also do this. We can say, okay, this is going to be equal to the same thing, plus Kuzdar's potential outcome if he did not get health insurance, okay, which we can't see, but what we can do is add and subtract it, because adding and subtracting one thing is the same thing as adding a 0, right? So this equality holds even if you can't see exactly why we want to put this in here, but it does hold, right? Because this is 0 and anything is equal to itself plus 0. If we continue on, well, now we see why it was worth it to kind of do that trick and put that 0 in there. We can just rearrange terms, okay? And you can do this on a pen and paper, right? Just kind of move over the y0 Kuzdar and the minus y0 Kuzdar. We put this guy, he's going to end up over here, and this guy's going to end up here. And we put the parentheses around these folks, and it ends up with these two differences. Okay, so what we're saying, again, is that we started out just by comparing the actual values of health for these two folks, Kuzdar, Maria, and in the end we said the comparison of the actual values is composed of these two comparisons of potential values, right? So we can actually see that the unobservable, alternate realities that don't happen are kind of buried in here. And again, our goal is we want to know this. What is the actual impact of health insurance for Kuzdar, who got it, right? We don't, we want to get rid of this, which is what we call selection bias, okay? So a comparison of the observed values, to restate this, the observed values between Maria and Kuzdar gives this. So the first piece is the actual causal effect. That's what we're after, okay? The second piece is what we call selection bias, or the lack of comparability between Kuzdar and Maria, right? We said Maria is just healthier, even without insurance, right? So her Y0, I think we said was 5, and Kuzdar's was 3, right? So this comparison is in here, this -2 here, and that's why we ended up with a -1, right? We did 1 minus 2, just doing the simple comparison, right? We ended up with a -1 for this, and this is why, because there's actually a true treatment effect in there of 1, and the selection bias term, which is -2. And all this does is, again, to formalize this intuition about apples to oranges and apples to apples comparisons, right? We're showing that comparing the observed difference in means, or differences in outcomes rather, for individuals is going to be confounded or contaminated by this other difference, right? So in other words, Kuzdar and Maria would have had different health outcomes even if they did not differ in their health insurance status, okay? So the failure of the apples to apples comparison comes in the fact that these two things, right, this second piece, this term here, these two things are not equal, right? There's a baseline difference in health that would have been observed even if these two folks did not differ in health insurance. Like Maria is always going to be healthier, right? So there's a problem when it just happens to be that the sicker people are the ones who are more likely to get insurance. The problem is that it confounds our comparison. So we call this problem selection bias, okay? That's why this is called bias in randomization. And we say that in comparison between groups with different values of the independent variable or treatment, selection bias is the difference in Y0i, so the difference in the potential outcome under the non-treatment status. So in this case, the difference in health that would have been observed if they did not get health insurance. So that difference in Y0i between those who did not take the treatment and those who did, okay? So those who did not take the treatment and those who did. They have a difference in this thing. These things aren't equal. So that's what screws us up here. So for example, Y0 Kuzdar, that's what Kuzdar's health would have been had he not taken the treatment. He did take it, but this is out there still. And Y0 Maria is what Maria's health would have been had she not taken the treatment. She did not take the treatment, it turns out, so we can actually see this piece, but we can't see this piece. And so we don't know, in reality, when we deal with a real problem, we know there's probably an issue, like that the two things over there aren't comparable, but we can't actually see this, so we can't formally, know how bad it's going to be. But later on, we'll talk about how to fix it, regardless of what it is. So we call this selection bias because the bias here is deriving from the fact that those with different potential outcomes can select their treatment status. Okay? So what does that mean? So intuitively, right, who's going to be more likely to want to get health insurance? Probably people who are sicker. That's pretty plausible. And so who's going to be more likely to, say, enroll in a program that's supposed to help poor people get out of poverty? Probably really motivated people, right? Or people who would really benefit from that program. Who's going to be more likely to get a college education? People who are more motivated, right? They're going to be different from the general population, or rather different, crucially, from the people who do not who decide not to go to college, not to enroll in a program, right? So this problem is everywhere, selection bias. So again, what we see, the difference in the actual health between Kuzdar and Maria, is the sum of the thing we want to estimate and some bias we want to eliminate. Now note, this is different. This type of bias is different than just sampling error, right? That can be, sampling error is a different problem. That's alternative explanation number one, okay, or skeptic number one. We can get rid of that relatively easily. We just get more data. Okay, that's the law of large numbers will kick in. It'll say sampling errors cancel out as n gets big. Okay. Now we're going to use that. We're going to use the law of large numbers. You'll see it's in the Angress book. It's necessary, but it's not sufficient for dealing with this other problem, which is selection bias. So 1 million, or infinity number of apples to oranges comparisons, is not necessarily better than one apples to oranges comparison. Okay, it's just going to multiply that problem. Doesn't get rid of it just by gathering more data. Okay, even though selection bias is its own problem that's distinct from the sampling error problem, you know, the way the media reports on studies, right, would have you believe that, you know, sampling error is really the only thing to worry about, right? But it happens to be the case that there's countless large N studies out there, so studies, you know, full of thousands of people or representative samples even, but they're still hopelessly plagued by this problem of selection bias. Okay, so don't be fooled when someone says, you know, I have a lot of data. That doesn't mean everything is okay, that you should believe what they're saying. You know, journalists are trained to report that a study is large, but they largely don't, you know, they aren't equipped to explain how the study accounts for this other problem of selection bias. Partly that's because, you know, what exposure to journalists have to statistics is probably stops at, you know, the t-test. And the t-test, again, is about sampling error, whereas this is a different problem.